The largest structures in our universe are vast, empty bubbles spanning hundreds of millions of light years. These cosmic voids are not just empty space. They are dynamic regions that may hold the key to understanding why our universe is expanding at an ever-increasing rate. By the end of this journey, you will see how these colossal pockets of nothing could unlock the cosmos's greatest secret. We will explore how their immense growth might be driving the acceleration of the universe and why they challenge our most fundamental theories. What do you believe is truly hidden within this cosmic emptiness? Our universe is structured like a colossal spiderweb, glimmering with the light of galaxies. These galaxies are not scattered randomly. They form immense walls and filaments, tracing out the grand architecture of the cosmos. But between these brilliant strands lie the voids, vast and profoundly dark. A cosmic void is simply a region of space with far less matter than the average across the universe. While not a perfect emptiness, these are the deserts of the cosmos. You might find only sparse clouds of hydrogen gas, the unseen presence of dark matter, and the occasional lonely dwarf galaxy drifting in the immense gloom. The scale of these voids is almost impossible to grasp. The Boötes void, for instance, is a spherical region of near-nothingness so large that it would take a beam of light hundreds of millions of years to travel from one side to the other. If our Milky Way sat at its center, we might not have even known other galaxies existed until the 1960s. This foundational understanding of what a void truly is, these immense bubbles of near emptiness, is the first step toward appreciating their profound influence. The story of how we first discovered these staggering gaps in the cosmos began with a simple yet revolutionary act of mapping the heavens. Mapping the heavens in 3 dimensions revealed a truth more startling than anyone had anticipated. In the late 1970s and early 80s, astronomers like Robert Kirshner were pioneering new surveys of the sky, meticulously plotting the positions of thousands of galaxies. They expected to find a roughly uniform distribution, a cosmic soup of stars. Instead, their maps told a different story. They revealed staggering, cavernous regions where galaxies were almost entirely absent. It was like charting the continents of Earth only to find immense, unexpected oceans between them. The discovery of the Boötes void was a landmark event that sent ripples through the scientific community. Here was a spherical emptiness so vast it defied the prevailing models of the cosmos. The initial reaction was one of disbelief. Could this truly be real, or was it merely an artifact of incomplete data? This was not a minor curiosity. It represented a fundamental paradigm shift, forcing cosmology to abandon the idea of a smooth universe and embrace a new reality, one of a complex cosmic web. This shift challenged the very foundations of gravitational theory and how we understood structure to form over billions of years. From their very discovery, these voids have been at the forefront of challenging our cosmic assumptions, pushing us toward a deeper, more intricate understanding of the universe's architecture. And it is this same disruptive nature that now positions them as a potential key to the universe's most profound behavior. Its accelerating expansion driven by the mysterious influence of dark energy. For decades, the leading explanation for the universe's accelerating expansion has been a mysterious repulsive force known as dark energy. This enigmatic energy is thought to be woven into the very fabric of space, pushing galaxies apart. But what if our interpretation has been pointing to the wrong kind of emptiness? Could the force we call dark energy be an illusion, a cosmic average created by the explosive growth happening inside voids themselves? To understand this, we need to visualize a grand cosmic tug of war. In the dense regions of the universe within great clusters of galaxies, gravity is immensely powerful. It pulls matter together, acting as a brake on the expansion of space in those crowded neighborhoods. Now, shift your perspective to the voids. These are the underdense regions, the cosmic deserts where gravity's pull is exceptionally weak. With so little matter to hold it back, the space inside a void is free to expand much faster than the universe's average rate. Imagine two balloons, one tightly constrained by a net and the other inflating freely. The freely expanding balloon will always grow faster. This is the fundamental idea. The overall acceleration of our universe may not be driven by a mysterious new force in every location, but could instead be the statistical outcome of most of space residing within these fast-growing voids. It is a compelling, almost Copernican shift in thinking, forcing us to look not at the bright nodes of the cosmic web, but at its dark, empty chambers for answers. And this leads us directly to a pivotal question. What specific property of these voids gives them such an outsized influence on the fate of everything? The emptiness of a cosmic void is not a passive absence. It is a physical environment with its own unique rules. To grasp their power, we must look at the specific properties that define these regions. First, consider their density, or more accurately, their profound lack of it. A typical void contains less than 1/10 of the universe's average matter. Where a galaxy cluster is a bustling metropolis, a void is an expanse of scattered farmland, with light years of near vacuum between isolated outposts. This incredible sparseness is what sets the stage for everything that happens within. Surrounding this emptiness are the void walls. These are the dense filaments and great walls of the cosmic web, acting as the boundaries of these vast bubbles. Picture a soap bubble floating in the air. The film of the bubble is its wall, a defined, structured surface that contains the empty space within. In the cosmos, these walls are made of galaxies and dark matter, a brilliant, tangled web that holds the void in its place. Inside the void, gravity behaves in a counterintuitive way. Because there is so little matter within the void itself, its gravitational pull is exceptionally weak. The real power lies in the densely packed walls surrounding it. The immense gravitational tug from these surrounding regions effectively pulls matter away from the void's center. It is not that the void is actively pushing matter out, but rather that everything inside is being gently, yet irresistibly, drawn toward the denser regions outside. This creates a unique gravitational landscape where the very fabric of space is less tethered, less held back. This is the critical point. With gravity's brakes all but released, the space inside a void can expand at a faster rate than the universe's average. The physics of expansion operates on a different set of rules here, in these deserts, than it does in the crowded galactic cities. It is within these near-empty bubbles that the expansion of the universe finds its freest, most unhindered expression. But if these regions are so empty and dark, how do we even begin to see them? Detecting these vast regions of nothingness requires some of the most ingenious techniques in modern astronomy. How do you map an absence? You do not look for the void itself, but for the traces it leaves on everything around it. The primary method is to meticulously map the things we can see, the galaxies. Projects like the Sloan Digital Sky Survey have undertaken this monumental task, charting the positions and distances of millions of galaxies. By plotting these points in 3 dimensions, the cosmic web emerges in stunning detail, and the voids are revealed as the great, dark bubbles between the glittering filaments. It is an exercise in cosmic cartography where the empty spaces are defined by the borders of the populated ones, but astronomers can go further, probing the voids more directly. One method involves studying the ancient light from the cosmic microwave background, the afterglow of the Big Bang. As this light travels across the universe on its way to us, it passes through these vast voids. When a photon enters a void, it must climb out of the gravitational well created by the surrounding dense walls. In a universe dominated by matter, the photon would regain that energy on the way out. However, in our accelerating universe, the void's gravitational potential weakens as the photon is traveling through it. The photon escapes with a little extra energy, leaving a specific, subtle imprint on the background radiation. This is known as the integrated Sachs-Wolfe effect, a tiny but measurable signature that provides direct evidence of the void's gravitational influence on the fabric of spacetime itself. Another technique peers into the voids using distant beacons called quasars. The intense light from a quasar located far beyond a void shines through the sparse gas within it. Elements like hydrogen within the void absorb specific wavelengths of this light, creating a complex pattern of dark lines in the quasar's spectrum. This pattern, whimsically called the Lyman alpha forest, acts like a barcode. By decoding it, scientists can map the distribution and density of the incredibly diffuse gas that drifts within these empty regions, giving us a chemical census of the cosmic deserts. These sophisticated tools, from galaxy surveys to the echoes of ancient light, allow us to see the invisible and measure the immeasurable. With these detailed maps in hand, we can begin to investigate the surprising life cycle of a void itself. These vast cosmic deserts were not always so empty. They have a life story, a dynamic evolution that unfolds over billions of years. It all began in the first fleeting moments after the Big Bang, when the entire universe was a seething, dense soup of energy. At this quantum scale, tiny fluctuations in density were imprinted upon the fabric of spacetime itself. Think of the surface of a very still pond suddenly disturbed by a light rain. Each raindrop creates a tiny ripple, a minute variation in the water's surface. In the early cosmos, these ripples were the seeds of all future structure. The slightly denser spots had a stronger gravitational pull, drawing in more and more matter over eons, eventually collapsing to form the first galaxies and the great clusters we see today. But what about the slightly less dense spots? These were the embryonic voids. While gravity was busy building up the dense regions, it was also subtly evacuating these underdense patches. Matter was slowly siphoned away, drawn toward the growing gravitational wells of the clusters and filaments. Over immense spans of time, these small pockets of nothingness began to grow, not by acquiring anything, but by losing what little they had. They expanded and emptied out, becoming ever more profound in their emptiness. This growth is an active, ongoing process. Small, irregular voids often merge with their neighbors, like soap bubbles coalescing into one larger, more spherical bubble. This is how the colossal supervoids we observe today are formed. This merging and growth is not a quiet affair. It actively sculpts the cosmos. As a void expands, it effectively pushes matter ahead of its boundaries, herding galaxies into the dense walls and filaments that make up the cosmic web. The void is not just an empty space, it is a cosmic sculptor carving out the architecture of the universe itself. This entire life cycle, from a quantum whisper to a dominant feature of the cosmos, is what makes their role in universal expansion so compelling. Their evolving nature suggests their influence is not static but growing. This profound idea leads us directly to a specific and controversial theory that places these growing voids at the very heart of cosmology's greatest mystery. This very growth of cosmic voids may be rewriting the laws of cosmology from within. A provocative idea known as the Backreaction Hypothesis presents a direct challenge to the long-standing dark energy model. It proposes a radical shift in our thinking, suggesting that the accelerating expansion of the universe is not driven by a mysterious, unseen energy. Instead, it could be an illusion, a cosmic averaging effect born from the sheer scale and emptiness of these voids. The theory hinges on a fundamental mismatch between the local and the global views of space. In a perfectly smooth universe with matter distributed evenly, expansion would proceed at a steady, predictable rate everywhere, but our universe is not smooth. It is a tapestry of extreme contrasts, with dense clusters acting as anchors and vast voids expanding with incredible freedom. The backreaction concept argues that the rapid, unhindered growth within these voids does not just happen in isolation. It backreacts on the overall geometry of the cosmos, pulling the average expansion rate upward. Imagine trying to calculate the average speed of traffic on a continent. If you only measured cars in crowded city centers, you would get one number. But if you then accounted for the vast, open highways where vehicles can travel at high speed, the continental average would rise significantly. The voids are the cosmic highways, and their faster expansion is what we may be mistaking for a universal force called dark energy. This idea forces us to confront a foundational pillar of cosmology, the cosmological principle. This principle states that on the largest scales, the universe should look roughly the same in every direction, homogeneous and isotropic. Voids and clusters in their individual forms seem to violate this. They create a universe that is lumpy and structured, not smooth. The critical question is whether these structures are merely small wrinkles on an otherwise uniform fabric, or if their collective gravitational influence is so profound that it actually warps the fabric itself on a global scale. The Backreaction Hypothesis boldly asserts the latter. It suggests that the cosmos's own intricate architecture, the very web of voids and filaments we have mapped, is the true engine of its acceleration. This transforms our understanding of the universe from a passive stage governed by invisible forces into a dynamic, self-influencing structure. If the voids themselves are the key, then the next logical step is to ask how we can test this extraordinary claim against the established order. The cosmological principle is a comforting idea, a rule of cosmic fairness that has guided our view of the universe for a century. It tells us that on the grandest scales, the cosmos is homogeneous and isotropic. It should look roughly the same in every direction, a smooth and uniform tapestry. Yet when we point our telescopes at the sky, we see something profoundly different. We see a universe of staggering contrast, defined by the very voids and filaments that shatter the illusion of smoothness. The existence of a void like the Boötes void, a spherical emptiness hundreds of millions of light-years across, forces a difficult question. Is this simply a rare statistical fluke, a once-in-a-universe anomaly, or is it a sign that the principle itself is cracking under the weight of new evidence? If such mammoth structures are more common than our models predict, they point toward a universe that is fundamentally inhomogeneous. Its properties, including the very rate of expansion, could depend on where you are. This is not a small adjustment. It strikes at the heart of how we interpret everything. Our entire understanding of cosmic expansion, including the evidence for dark energy, relies on the assumption that the cosmological principle holds true. We assume that a supernova in a distant galaxy tells us about the universal rate of expansion. But what if that light traveled through a region of space so empty that its expansion rules are entirely different? The interpretation of that data would be fundamentally flawed. This potential paradigm shift is not just philosophical, it demands hard evidence. Astronomers are now searching for the definitive test. looking for subtle patterns in the cosmic microwave background or statistical anomalies in the distribution of millions of galaxies that could reveal whether we live in a truly smooth universe, or one whose magnificent lumpiness has been writing its own rules all along. This ghostly whisper from the ancient light of creation offers a direct test. The story is written in the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. As these primordial photons travel for billions of years to reach our telescopes, their journey is not a simple one. They must traverse the evolving cosmic web, passing through both dense clusters and the vast, empty voids. According to Einstein's theory of general relativity, a photon gains energy as it falls into a gravitational well, but it should lose that exact same amount of energy as it climbs back out. In a universe dominated purely by matter, the net effect would be zero. The photon would arrive with the same energy it started with, but our universe is not just matter. If the expansion is accelerating due to dark energy, or because of the backreaction from growing voids, the gravitational landscape itself is changing during the photon's long voyage. When a photon enters a void, it climbs out of a gravitational well that is actually becoming shallower with time because the void is growing. The photon does not get all of its energy back. It escapes with a little less, and this loss of energy manifests as a tiny, cold spot in the map of the cosmic microwave background. This is the integrated Sachs-Wolfe effect. It is an incredibly subtle signal, a temperature drop of only a few millionths of a degree. The search for it is a monumental task, requiring astronomers to cross-reference the positions of known supervoids with the most precise maps of the CMB ever created. The initial results have been tantalizing. Some studies have indeed found a correlation. They point to specific, massive voids that appear to be shadowed by corresponding cold spots in the ancient light. For proponents of the backreaction theory, this is a potential smoking gun, evidence that the voids are not just expanding, but that their growth is actively reshaping the cosmos in a way that mimics dark energy. Yet the signal remains weak and hotly debated. Other analyses find the correlation to be statistically insignificant, perhaps just a chance alignment in the cosmic noise. This is the cutting edge of cosmology in action, a fierce and meticulous detective hunt for a whisper in the static. The very controversy highlights how differently voids behave depending on which cosmic rulebook you use. In the standard model, their influence is localized and dark energy is the universal driver. In alternative theories like backreaction, the voids themselves are the primary actors on the global stage, their collective growth writing the story of cosmic acceleration directly into the fabric of space. The ultimate battleground for these theories lies not only in our telescopes, but within the calculations of supercomputers. Cosmologists build entire universes inside these machines, using the standard model known as lambda cold dark matter. This framework includes both dark matter to provide cosmic structure and dark energy to drive acceleration. When these simulations run, they do produce a universe that looks familiar, complete with a cosmic web and vast voids. The question is one of precision. Do the virtual voids match their real-world counterparts in every detail, from their sheer size and spherical shape to how they are scattered across the cosmos? The answer appears to be a tentative no. The voids in our observed universe seem to grow larger and more perfectly spherical than the standard model typically predicts. This subtle mismatch is a critical clue. When researchers run alternative simulations, perhaps those that modify the laws of gravity itself or rely purely on the backreaction from growing emptiness, they can produce a different statistical portrait of the void population. The number of voids of a given size, known as the size function, and their shapes become a powerful diagnostic tool. It is like having two different blueprints for a sponge. Both might show a porous structure, but the precise size and arrangement of the holes will tell you which engineer drew the plans. These cosmic sponges, with their specific distribution of empty spaces, are testing our most fundamental laws. And this theoretical struggle finds a perfect focal point in one of the most perplexing structures ever mapped, a void so immense it has been called a supervoid. One of the coldest mysteries in the cosmos is etched into the oldest light we can see. Known as the CMB cold spot, this unusually large and frigid patch in the cosmic microwave background has puzzled astronomers for years. It is a region of sky significantly colder than the surrounding afterglow, a giant cosmic chill that standard models struggle to explain. Could this be the signature of a void so immense it defies our expectations? Some researchers believe so, pointing to the potential influence of a colossal structure dubbed the Eridanus supervoid. The theory is elegant. If a truly gigantic underdense region lies along our line of sight to this part of the CMB, the integrated Sachs-Wolfe effect could be at work. A photon passing through such a vast emptiness would lose a measurable amount of energy as it climbed out of the void's weakening gravitational well, arriving at our telescopes as a colder, dimmer whisper from the early universe. The hunt for this phantom void began, a search for a specific absence that could explain a specific coldness. The results, however, were deeply mixed. Astronomers did indeed identify a large underdense region in the direction of the Eridanus constellation. It is a genuine supervoid, a bubble of cosmic nothingness stretching an incredible 1.8 billion light-years across. Yet for all its staggering size, it appears to be too shallow. Its lack of density is not profound enough to generate the dramatic temperature drop we observe in the cold spot. It is as if we found a crater, but one not nearly deep enough to account for the size of the impact. This discrepancy leaves us at a fascinating crossroads. The Eridanus supervoid might contribute to the cold spot, but it cannot be the sole cause. Perhaps the void is larger or emptier than our current maps can detect, its true dimensions hidden in the sparse data between galaxies. Or the cold spot might be a rare statistical fluke, a colossal ripple in the primordial fabric of space with no need for a void to explain it. This single case study encapsulates the entire challenge of modern cosmology. It shows the immense difficulty of connecting a specific, local structure to a global phenomenon, and it highlights the precision required to move from tantalizing correlation to definitive cause. Beyond the mystery of the cold spot, the very existence of voids as large as the one in Eridanus presents its own profound puzzle. Their sheer scale pushes against the limits of what our standard models of the universe should allow. The sheer scale of these cosmic voids presents a deep and growing puzzle. When we look at structures like the Boötes void, or consider the staggering possibility that our own Milky Way resides inside a vast local underdensity known as the KBC void, we are forced to confront the limits of our standard cosmic model. This model, built upon the idea of a specific pattern of initial quantum fluctuations, predicts a certain statistical distribution for the sizes of voids. It suggests there should be a natural limit to how large these empty bubbles can become before they become vanishingly rare, yet the observations seem to be pushing against that limit. The existence of so many gigantic voids, some spanning over 1 billion light-years, feels like finding multiple craters far larger than any known impactor should leave behind. Are these just statistical flukes, rare but permissible outliers in a vast and lumpy cosmos? Or is their prevalence a clue that the initial conditions of the universe were not as random as we thought, perhaps seeded by a more complex, non-Gaussian pattern? This is not an abstract debate. The size of these voids is intimately connected to the expansion rate of the universe itself. a void's growth is governed by the gravitational tug of war between its empty interior and its dense walls. If voids are consistently larger than our models predict, it implies that this gravitational dynamic is playing out differently, that the fabric of space within them is expanding faster or more freely than our equations account for. This could mean that the backreaction from these growing emptinesses is a more significant force than we have realized, effectively pulling the universe apart from the inside out. The very emptiness that defines these regions may be holding the key to understanding why everything is moving away from everything else at an ever-increasing pace. The search for answers now leads us to the most radical frontier of all, where the very laws of gravity themselves are called into question. This very emptiness, the defining feature of a cosmic void, can be transformed into one of the most powerful measuring tools in cosmology. Imagine a ruler so vast it spans hundreds of millions of light years, a ruler etched into the fabric of space itself. This is the principle behind using voids as standard rulers, a technique known as the Alcock-Paksinski test. The core idea is beautifully simple. If we know the true, intrinsic shape of a typical cosmic void, we can measure how the expansion of the universe has distorted its appearance from our perspective. Most voids are not perfect spheres. They tend to be slightly elongated, like a stretched-out ellipsoid. Crucially, we believe we understand the statistical average of this natural shape from our simulations and models. Now picture such a void located at a great distance, its light taking billions of years to reach us. As that light travels, the universe continues to expand. This expansion does two things. It stretches the void's appearance along our line of sight, making it seem longer. Simultaneously, it also affects its apparent width across our line of sight. The difference between these two distortions is the key. By comparing how much the void appears stretched in the radial direction compared to the transverse direction, we can directly measure the expansion rate of the universe at the time the light left that void. It is like watching a familiar object, a known shape, recede from you in a flowing river. The way its shape appears to warp tells you everything about the current of the river itself. This direct measurement allows cosmologists to pin down the Hubble parameter, the number that describes how fast the universe is expanding across different epochs of cosmic history. Each void becomes a data point, a fossil record of the universe's expansion at a specific moment in time. By collecting thousands of these measurements, we can chart the detailed history of how the expansion rate has changed, offering incredibly precise constraints on the nature of dark energy. Does its strength remain constant, or has it evolved over billions of years? The geometry of these growing emptinesses may hold the definitive answer. This transforms voids from passive subjects of curiosity into active instruments, the ultimate cosmic probes that allow us to take the universe's vital signs. The profound emptiness of a cosmic void is not what it seems. While these regions are nearly barren of the bright, shining galaxies we can see, they are not a perfect vacuum of matter. They are, in fact, filled with the invisible architecture of the cosmos, dark matter. This mysterious substance, which does not emit or absorb light, forms a vast, smooth, and incredibly diffuse halo within the void's boundaries. It is the ghostly skeleton upon which the visible universe is built, and its presence is felt most keenly in these empty places. The way a lone, isolated galaxy drifts through the immense darkness of a void is not a random journey. Its path is governed by the subtle yet immense gravitational pull of this unseen dark matter. Even in near nothingness, gravity's hand is at work, sculpting the motion of the single galaxy and shaping the evolution of the void's dense walls over billions of years. This gives voids an extraordinary purpose. They become a pristine laboratory for dark matter physics. In the standard model of cosmology, we assume cold dark matter made of slow-moving heavy particles. This model predicts a specific pattern for how voids should form and evolve, creating a certain distribution of sizes and shapes. But what if dark matter is different? Consider an alternative like warm dark matter composed of lighter, faster-moving particles. In such a universe, the small-scale structures that are the seeds of voids would be smoothed out. The result would be a cosmos with far fewer but much larger voids. The very population of these empty regions, their statistics and characteristics, becomes a powerful test. By meticulously counting and measuring the voids we observe, we are effectively conducting an experiment on the fundamental nature of the invisible stuff that makes up most of the universe's mass. The darkness within these voids may hold the key to illuminating the darkness that binds everything together. Deep within the cosmic web, there is a subtle rhythm, a fossilized echo of the universe's first moments. This rhythm is known as Baryon acoustic oscillations. In the incredibly dense, hot plasma of the infant cosmos, pressure waves moved outward from every point, much like sound waves traveling through air. These waves carried both ordinary matter, the baryons, and radiation in a synchronized dance. Then, in a flash of cosmic cooling, the universe became transparent, freezing these waves in their tracks. The result was a single, preferred scale imprinted on the cosmos, a standard ruler etched into the distribution of matter. We see its signature today as a subtle tendency for galaxies to be separated by a specific distance, about 500 million light-years. It is the universe's own resonant frequency, a whisper from the beginning of time, but this whisper is not just carried by the galaxies. The same preferred scale is stamped onto the void network itself. The distances between the centers of neighboring voids are not random. They, too, carry this ancient rhythm. The empty spaces are arranged in a pattern that mirrors the original oscillations. This offers a profound advantage for cosmologists. In the crowded, violent environment of galaxy clusters, gravity has been hard at work for billions of years, violently pulling matter together and blurring the pristine signal. The Baryon signature there can become smudged like a fingerprint on a dusty surface, but within the quiet, calm emptiness of the voids, this fossil imprint remains remarkably clean. With so little matter to create complex gravitational disturbances, the signal is preserved with stunning clarity. By measuring the distribution of voids, we can measure this cosmic ruler with incredible precision, providing an independent and powerful check on our maps of cosmic expansion. This silent network of emptiness becomes a crystal-clear lens through which to view the universe's deepest history. And if the voids themselves can act as such precise instruments, what strange physics might be occurring within their near-perfect vacuum? Even in the deepest cosmic deserts, isolated islands of stars hold on. These are the void galaxies, solitary systems adrift in an ocean of near-nothingness. Their existence paints a different picture of cosmic life, one defined by profound isolation rather than the crowded dynamics of a galactic city. While a galaxy in a dense cluster is constantly jostled and merged with its neighbors, a void galaxy evolves in quiet solitude. It is a galactic hermit following a slower, more introspective path through cosmic history. This isolation has profound consequences for its life cycle. Shielded from the violent gravitational tides of a crowded neighborhood, a void galaxy experiences far fewer mergers and collisions. Its evolution is not punctuated by dramatic, disruptive events, but is instead a story of steady, internal growth. This peaceful existence allows it to hold onto its most precious resource, cosmic gas. In the dense intracluster medium of a galaxy group, this raw material for star formation is often brutally stripped away, leaving galaxies gas poor and fading. But in the void, there is no such hostile environment. The galaxy retains its vast reservoirs of primordial hydrogen, the fuel for new suns. The result can be a surprisingly high rate of star formation. These isolated systems often become vibrant stellar nurseries, their spiral arms blazing with the blue light of young, massive stars. They are not the faded relics one might expect in such an empty place, but can be brilliant, gas-rich powerhouses. This makes them a cosmologist's dream, a perfect control sample. By studying these galactic hermits, we can see what a galaxy is like when left mostly to its own devices, free from the complex influences of its environment. They offer a pure view of intrinsic galactic processes, revealing the fundamental rules of how a galaxy lives and grows when the universe just lets it be. The profound emptiness of a cosmic void is an illusion. These great bubbles are not truly empty. They are filled with a ghostly, tenuous fog known as the intergalactic medium. This is not a gas you could ever breathe. It is far more diffuse than the best vacuum we can create on Earth. Yet, despite its ethereal nature, this intergalactic medium holds a stunning secret. It is the primary reservoir of all the normal matter in the universe. The stars in every galaxy, the planets orbiting them, and everything we are made of, represent only a small fraction of the cosmos's ordinary stuff. The vast majority of it, the bulk of the atoms that were forged in the Big Bang, are floating out here in the darkness between the voids, in this incredibly sparse sea of ionized hydrogen. How can we possibly detect something so perfectly transparent? The answer lies in using the universe's most brilliant flashlights, quasars. When the intense beam of light from a distant quasar travels for billions of years on its journey to our telescopes, it passes through these vast cosmic deserts. The hydrogen atoms in the intergalactic medium act like filters, absorbing very specific wavelengths of that light. This creates a complex barcode of dark lines in the quasar's spectrum, a pattern scientists poetically call the Lyman alpha forest. Each line is a shadow cast by a different cloud of hydrogen, a fingerprint of the gas at a specific distance. By decoding this forest of lines, astronomers can map the density and temperature of the gas throughout the void, taking a chemical census of the cosmic wilderness. This ghostly gas is more than just a relic, it is a cosmic historian. Its temperature and ionization state are a permanent record of the universe's energetic past. The gas is heated and ionized, stripped of its electrons, by the ultraviolet background radiation that fills all of space. This radiation is the collective glow from countless quasars and massive stars, a fossil light that has been bathing the cosmos for eons. By reading the state of the intergalactic medium, we can decipher the history of this radiation, understanding when the first stars and galaxies flooded the universe with their intense light. Furthermore, the gas bears the scars of immense feedback processes. When a supernova explodes or a supermassive black hole at the heart of a galaxy erupts, it sends colossal shockwaves of energy out into the void. These events can reheat the intergalactic medium, altering its temperature and density in ways that are preserved for billions of years. This tenuous fog is therefore the key to completing the cosmic inventory of ordinary matter, and to understanding how the violent lives of galaxies have shaped the serene emptiness that now surrounds them. This next leap in understanding will come from the eyes of a new generation of cosmic cartographers. The Nancy Grace Roman Space Telescope, set to launch in the latter half of this decade, is designed to perform a monumental task. It will survey vast stretches of the sky with a field of view 100 times larger than that of the Hubble Space Telescope. This is not about taking pretty pictures of single galaxies. Its mission is to map the cosmos in 3 dimensions with staggering speed and precision. charting the positions and distances of billions of galaxies. From this immense data set, the cosmic web will emerge in a level of detail we have never witnessed, and with it, a crystal-clear census of the void network. We will not just see the largest voids, we will catalog millions of them, understanding their true distribution, their perfect spherical shapes, and how they cluster together across the expanse of the universe. This statistical power is the key to turning speculation into science. With such a vast sample, we can perform the Alcock-Paksinski test with incredible precision, using the shapes of these voids as standard rulers to measure the expansion history of the universe across billions of years. Simultaneously, a different kind of eye will be opening on the ground. The Square Kilometre Array, or SCAR, is not a single dish but a forest of antennas spread across South Africa and Australia, forming the most sensitive radio telescope ever conceived. Its great power lies in its ability to see the unseen. It will map the distribution of neutral hydrogen gas across the cosmos, tracing this fundamental building block of matter from the early universe to the present day. This allows us to peer directly into the hearts of voids, measuring the density and flow of the tenuous gas that drifts within these empty regions. It will reveal how the void's own intergalactic medium is shaped by the expansion of space and the gravitational pull of the surrounding walls. Together, these observatories will provide a dual view of cosmic emptiness. Roman will map the galaxies that define the void boundaries, while the SKA maps the ghostly gas within. The combined data will be nothing short of monumental, a flood of information that will allow us to measure the integrated Sachs-Wolfe effect with unprecedented confidence. We will see with definitive clarity whether the cold spots in the cosmic microwave background align perfectly with the positions of the largest supervoids. This is the ultimate test. Will the data show that the acceleration is a smooth, universal force, as the dark energy model suggests? Or will it reveal that the lumpy, growing voids are backreacting on the cosmos, creating the illusion of dark energy through their collective gravitational influence? The answers are written in the expanding darkness, and we are finally building the instruments to read them. A deep crack has appeared in the foundation of modern cosmology. It is known as the Hubble Tension, and it is a crisis of measurement. When we look at the ancient universe by studying the cosmic microwave background, we get one very precise number for how fast the cosmos is expanding today. Yet, when we measure the contemporary universe using brilliant supernova as mileposts, we get a different, faster number. The two most trusted methods for taking the universe's pulse are in direct, stubborn disagreement. This is not a small error. It is a significant discrepancy that has resisted every attempt at reconciliation, suggesting we might be missing something fundamental about the physics of the cosmos. One of the most provocative solutions points directly back to the voids. The idea is both simple and radical. What if our entire galactic neighborhood, including the Milky Way, resides inside a colossal local void, a vast underdensity in the cosmic web? If we are living in a giant bubble of below-average density, the space around us would be expanding faster than the true global average, simply because there is less matter here to gravitationally slow it down. Think of it like being in a single, fast-flowing current within a wide, slower-moving river. From our limited vantage point, we would measure the speed of our local current and assume the entire river moves at that pace. Our local measurements of the Hubble constant, taken from supernova within this hypothetical void, would be artificially high. Meanwhile, the measurement from the cosmic microwave background reflects the true, average expansion of the entire universe, the wider river. This would resolve the tension not by changing the laws of physics, but by changing our understanding of our own place in the cosmic structure. the controversy surrounding this idea is intense. Could the void we potentially inhabit be large and empty enough to create the entire observed discrepancy? The required size would be staggering, perhaps hundreds of millions of light years across, a notion that challenges the cosmological principle itself. Yet, some studies suggest evidence for such a structure, often called the local hole or KBC void. Whether this specific void is the ultimate answer remains hotly debated, but the principle is what matters. It demonstrates with startling clarity that the emptiness surrounding us is not a passive backdrop. The local structure of voids can directly warp our perception of the entire universe, tricking us into seeing a cosmic acceleration that is, in part, a grand illusion of our own address. The roots of these colossal voids reach back to a time before time, to a realm governed by the strange rules of quantum mechanics. In the first fleeting fraction of a second after the Big Bang, the entire cosmos underwent a violent, exponential growth spurt known as inflation. During this incredible burst, the universe expanded faster than the speed of light, stretching a subatomic speck of space into a macroscopic volume. And in that seething, energy-filled vacuum, the seeds for all future structure were sown. Quantum fluctuations, tiny, temporary variations in energy that pop in and out of existence at the smallest scales, were suddenly stretched and frozen into the fabric of spacetime itself. These minute ripples in the primordial cosmos became the blueprint for everything. The slightly denser spots, the peaks of these ripples, eventually collapsed under gravity to form galaxies and clusters. But the troughs, the regions of slightly lower density, were the embryonic voids. This means the staggering emptiness of a supervoid hundreds of millions of light years across began as a whisper of quantum noise, a statistical hiccup magnified to a cosmic scale. The voids are not just empty space, they are fossilized quantum fluctuations. Their very existence creates a direct, tangible bridge between the bizarre, probabilistic world of the quantum and the grand, classical architecture of the universe we see today. This connection turns the entire network of voids into a powerful diagnostic tool. The specific pattern of these initial quantum ripples, their statistical signature, is predicted differently by various models of inflation. Some theories suggest the fluctuations were perfectly random, following a Gaussian distribution. Others propose more complex, non-Gaussian patterns, where fluctuations clump together in specific ways. How would these different blueprints manifest in the cosmos we observe today? The answer is written in the size and distribution of the voids. A universe born from simple Gaussian noise will produce a certain statistical family of voids, a predictable range of sizes and depths. But if the primordial fluctuations were non-Gaussian, the void population would tell a different story. We might see far more extremely large or extremely deep voids than the standard model allows, or perhaps voids that cluster together in unexpected ways. By meticulously counting and measuring the voids we see, we are effectively reading the fine print of inflation itself. We are testing which version of that primordial story best matches the cosmic structures we inhabit. Each vast, empty chamber is a time capsule, preserving a moment from the universe's first instant and offering us a unique window into the physics that shaped everything from the very beginning. These vast cosmic voids compel us to reconsider the very meaning of nothing. We often think of empty space as a passive stage, a simple backdrop upon which the drama of stars and galaxies plays out. But cosmology reveals this to be a profound illusion. The vacuum of space is not truly empty. According to quantum field theory, what we perceive as nothing is a seething, bubbling foam, a dynamic sea where virtual particles flicker in and out of existence in a relentless dance. In this light, a cosmic void is not an absence of physics, but a region where this fundamental, energetic activity is the dominant feature. This challenges our most basic assumptions about existence, suggesting that nothing is just as physically significant and active as something. The sheer dominance of these empty regions forces a humbling perspective shift. Our earthly experiences, centered on solid matter and bustling activity, are a cosmic anomaly. The universe is not made for us. It is overwhelmingly composed of vast, uninhabitable emptiness, a reality that voids make undeniably clear. They are the true norm, while the bright, dense islands of matter we call home are the rare exception. This realization can feel unsettling, yet it opens a door to a deeper, more accurate understanding of our place in the cosmos. We are not the center of the universe, but fleeting inhabitants of a tiny, fragile oasis in an immense and largely vacant expanse. This emptiness is not a void of meaning, but a canvas of physical potential, whose active nature might ultimately hold the key to the universe's grandest behavior. The standard cosmological model is not the only framework trying to make sense of these vast emptinesses. When we step beyond the familiar territory of dark matter and dark energy, the story of cosmic voids becomes even more intriguing. Consider modified Newtonian dynamics, or MUND, a theory that proposes our understanding of gravity itself is incomplete. In a MUND universe, there is no dark matter halo subtly filling the void. The gravitational dynamics in these underdense regions would be governed by a different set of rules entirely. Without the invisible scaffolding of dark matter to shape them, voids in a MONDian cosmos might look profoundly different, perhaps growing to even larger sizes or developing more sharply defined boundaries. Their very distribution across the sky would be a direct test, a unique fingerprint left by a modified law of gravity. Then there are the more radical approaches like timescape cosmology, which fully embrace the universe's lumpy nature. In this view, voids are not mere features on a smooth background. They are the dominant architecture, and their collective expansion is the primary driver of the cosmos's behavior. The average expansion rate we measure is not dictated by a mysterious energy, but is literally the combined effect of fast-expanding voids and slow-expanding clusters. The vacuum of a void and the heart of a galaxy cluster would not just be different neighborhoods, they would be regions experiencing fundamentally different flows of time and geometry, a concept that bends the mind. This theoretical diversity is not a weakness but a tremendous strength. It gives us a clear and powerful experimental path forward. By meticulously measuring the real void population, its size, function, shapes, and clustering, we can hold these competing blueprints up to the light of observation. Do the voids we see match the predictions of lambda cold dark matter, or do they align more closely with a universe where gravity is modified, or where emptiness itself defines the cosmic clock? Each vast, dark bubble becomes a question posed to the universe, and its answer could rewrite our most fundamental laws. These digital universes are born from pure mathematics and raw computational power. Scientists begin by defining a set of initial conditions, a digital snapshot of the early cosmos based on the faint patterns we see in the cosmic microwave background. They then program in the known laws of physics, primarily the relentless pull of gravity, and set the simulation in motion, watching as billions of years of cosmic evolution unfold inside a supercomputer over mere months. This process creates a virtual cosmos, a complete and self-consistent universe that can be explored in perfect detail. Researchers can pause, rewind, and zoom through this digital expanse, observing the formation of the cosmic web with a god's-eye view. They can tag every single virtual void, measuring its growth, its shape, and its interaction with neighboring structures with an accuracy impossible in our own messy, observable universe. This is the ultimate controlled experiment, What happens to a void if we change the strength of dark energy in the simulation? What if we modify the properties of dark matter, making it warmer or more interactive? The simulations provide the answers, showing how these fundamental ingredients sculpt the population of emptiness. They reveal the intricate gravitational dance where dark matter halos provide the invisible skeleton, and where the repulsive push of dark energy, or the lack thereof, either accelerates or restrains the void's growth. Without these virtual laboratories, our understanding of voids would be little more than educated guesswork. They are the proving grounds where theories of cosmic expansion are either forged in digital fire or quietly abandoned. Mapping the emptiness of the cosmos is far more complex than it first appears. A significant challenge begins with a seemingly simple question: where does a void actually end? Defining the boundary of these vast regions is not straightforward, and different research teams use different algorithms to find them in survey data. One method might define the edge at a specific density threshold, while another uses the geometry of the surrounding galaxy walls. This choice is not merely academic, it directly impacts every measured property of the void. The same cosmic bubble might be classified as larger or smaller, deeper or shallower, simply based on the definition used by the scientists. This creates a fundamental uncertainty that must be carefully accounted for when comparing results or testing theories. The problem deepens with an issue known as galaxy bias. When we build our beautiful three-dimensional maps of the cosmic web, we are not actually mapping the true underlying distribution of matter. We are mapping where the visible galaxies are located. We assume that these bright beacons trace out the unseen dark matter, the true cosmic skeleton. But this may not be a perfect correspondence. Galaxies might not form with equal efficiency in all environments, meaning some regions of dark matter could be more or less populated with visible galaxies than others. It is like trying to understand a city's population density by only counting the streetlights. The lights give you a general idea, but they do not tell you about every single person living in the shadows. This bias means a map of galaxy-defined voids might not perfectly align with the true underdense regions of dark matter, potentially skewing our interpretation of their growth and gravitational influence. Then there is the immense difficulty of detecting the subtle signals these voids produce. The imprint of the integrated Sachs-Wolfe effect, for instance, is incredibly faint, a temperature fluctuation of just a few millionths of a degree in the cosmic microwave background. Isolating this whisper from the cacophony of the cosmos is a monumental task. The signal can be contaminated by foreground light from our own Milky Way, by the faint glow of distant dust, or even by instrumental noise within the telescopes themselves. Disentangling the true cosmic chill of a void from this background static requires painstaking statistical analysis and cross-checks across multiple wavelengths of light. These are not minor technicalities, they are central hurdles in the scientific process. Acknowledging these uncertainties is not a sign of weakness in the theories, but a testament to the rigorous, careful work required to draw firm conclusions about the nature of our universe from the profound silence of its emptiest places. The ultimate destiny of our universe is written in its expanding emptiness. As dark energy's influence grows, the very architecture of the cosmos will begin to unravel. The great walls and filaments of the cosmic web, which have held their majestic structure for billions of years, will be stretched thin by the relentless acceleration of space itself. Those brilliant threads of galaxies will begin to snap, severing the connections between the last remaining islands of matter. The universe will transition from a glittering web to a sparse collection of isolated galaxy clusters, each one drifting alone in a sea of growing darkness. This is not a sudden event, but a slow, inexorable fading over trillions upon trillions of years. We are living in the cosmic noon, a golden age of structure and light, but the long twilight is already beginning. In this far future, the voids will not just be features of the cosmos, they will become the cosmos. Their expansion will be unopposed, their boundaries pushing ever outward as they merge with one another, creating ever larger bubbles of nothingness. What was once a complex sponge of matter and emptiness will simplify into a vast, dark ocean, with only the rarest of matter islands remaining. This connects the study of these empty regions directly to the fate of everything. The voids are not passive bystanders in this story. They are the dominant characters in the final act. Their growth is the mechanism by which the universe achieves its ultimate state of darkness and isolation. Every measurement we make of a void today is a glimpse into a future so distant that all stars will have long since burned out, and the universe will be a cold, silent, and profoundly empty place. This profound emptiness offers a perfect classroom for the universe's deepest lessons. Cosmic voids, these great bubbles of near-nothingness, provide a uniquely powerful way to grasp fundamental principles of physics that often feel abstract and distant. The sheer contrast they present makes the invisible forces shaping our cosmos suddenly tangible. Take the concept of gravitational potential, a cornerstone of Einstein's general relativity. It is difficult to visualize the warping of space-time around a single star or galaxy, but a void makes this warping visible on a grand scale. Picture the void as a vast, gentle hill in the fabric of the cosmos. The dense walls surrounding it are the steep slopes. A galaxy sitting near the edge of this emptiness will naturally roll downhill toward the greater mass of the walls, illustrating gravity's pull in a way a textbook equation never could. This is not just a theory, it is a dynamic process we can observe, where the void's own growth actively demonstrates how gravity behaves in regions of extreme low density. The expansion of space itself is another concept that voids make brilliantly clear. We often say the universe is expanding, but what does that truly mean for empty space? Voids show us, in a crowded galaxy cluster, gravity is strong, holding space tightly and slowing its expansion like a dense rubber sheet that is hard to stretch. Inside a void, however, that rubber sheet is loose and thin. With so little matter to provide gravitational resistance, the space within a void can stretch far more easily. It expands faster than the universe's average. This direct comparison between the fast-expanding voids and the slow-expanding clusters turns an abstract universal constant into a relative, measurable phenomenon that depends entirely on your environment. The stark architecture of the cosmic web, with its brilliant filaments and dark voids, acts as a ready-made diagram. It transforms the idea of large-scale structure from a complex computer model into a visual reality anyone can appreciate. We see the universe not as a random scatter of lights, but as an organized, interconnected system, a sponge of matter and emptiness whose very form tells the story of billions of years of gravitational evolution. Perhaps the most important lesson lies in challenging the cosmological principle, the assumption that the universe is smooth and uniform on the largest scales. A single, massive void like the Boötes void poses a direct question to this foundational idea. Is such a colossal structure a rare exception, or is it a sign that the universe is inherently lumpy? By studying the population and distribution of voids, students engage in a real, ongoing scientific debate. They are not just learning accepted facts, they are stepping into the process of discovery, seeing how observations force us to question and refine our most basic assumptions about reality. In this way, the study of nothing becomes a gateway to everything. By focusing on these great absences, we gain a clearer, more profound understanding of the something that governs all we see. The empty spaces teach us about gravity, the expansion of space-time, and the very nature of the cosmos, turning the most featureless parts of the universe into our most instructive teachers. Our language struggles to describe these vast cosmic deserts. We call them voids, a word that suggests a total and absolute emptiness, but this is the first and most persistent myth about them. A cosmic void is not a perfect vacuum. While they contain far less matter than the crowded filaments of the cosmic web, they are far from empty. They are filled with a sparse, ghostly fog of hydrogen gas, the raw material left over from the Big Bang. More significantly, they are permeated by the invisible presence of dark matter, which forms a smooth, diffuse halo throughout these regions. This unseen scaffolding is a crucial part of the void structure, its gravity subtly influencing the motion of the few galaxies that do reside within this immense gloom. Another common misunderstanding is that these regions are completely barren of galaxies. This is not quite true. While you will not find the brilliant, sprawling spiral galaxies that gather in great clusters, you can often find lonely, isolated dwarf galaxies drifting through the void. These small, often irregular systems are the hermits of the cosmos, evolving in quiet solitude, far from the gravitational turmoil of their larger cousins. Perhaps the most visually striking myth is the idea that a void is a hole in the universe, a literal tear or rip in the fabric of space-time. This is a powerful image, but it is not accurate. A cosmic void is not a puncture in reality. It is simply an immense region where the density of matter is significantly lower than the cosmic average. Think of it not as a whole, but as an incredibly large and underpopulated neighborhood within the continuous, unbroken fabric of space-time. The universe is not torn here, it is simply much, much quieter. Correcting these misconceptions is vital because it shifts our view of these structures from frightening absences to dynamic, physical environments. They are not cosmic errors, but essential features of our universe, whose unique properties may hold profound answers about the nature of reality itself. This profound emptiness echoes far beyond the equations of cosmology, resonating deeply within human culture and art. For centuries, artists have used the void not as a mere absence, but as a powerful presence. In the sparse, ink-wash paintings of East Asia, vast empty spaces are not left blank by accident. They are active elements representing silence, potential, and a profound respect for what is not said. The void becomes the space for the mind to wander, a visual echo of the cosmic deserts between galaxies. It is the sublime, the terrifying and beautiful awe we feel when confronted with an immensity that dwarfs our own existence. This artistic embrace of emptiness finds a parallel in modern literature and film. The chilling emptiness of deep space in science fiction is rarely just a backdrop. It becomes a character in itself, symbolizing the terrifying unknown, the profound isolation of the human condition, or the infinite possibilities that lie beyond our current understanding. These stories tap into the same primal fascination that drives astronomers to study cosmic voids, a confrontation with the ultimate other. Philosophically, these vast regions of nothingness challenge our most basic categories. What does it mean for something to exist? We are accustomed to a world defined by objects and interactions, yet the universe suggests that emptiness is not only real but dominant. A void forces us to confront the nature of non-existence itself. Is it truly nothing, or is it a something with its own physical properties, its own influence on the fabric of reality? This question bridges the gap between ancient philosophical inquiries and the cutting edge of theoretical physics. Drawing these connections reveals a beautiful truth. The study of cosmic voids is not a cold, technical pursuit isolated in an ivory tower. It is a deeply human endeavor, one that touches on the same fundamental questions that artists and philosophers have grappled with for millennia. Our scientific exploration of these great nothings is, in its own way, a search for meaning. It demonstrates how our quest to understand the cosmos inevitably circles back to understanding ourselves and our fragile, fleeting place within the immense and mostly empty expanse of all that is. This interdisciplinary dialogue enriches both science and the humanities, showing that the grand mystery of the cosmos is a story that belongs to all of us. The coming decade will transform these cosmic deserts from astronomical curiosities into fundamental laboratories. The central question is no longer if voids exist, but what their collective behavior is telling us about the laws of physics. Our next-generation telescopes are poised to deliver a verdict on the Backreaction Hypothesis, determining once and for all whether the accelerating expansion is a smooth force or a statistical echo of these growing emptinesses. Will the intricate geometry of millions of voids, measured with exquisite precision, reveal that their gravitational influence is strong enough to warp the entire cosmos? Simultaneously, voids offer a promising path to resolve the Hubble tension. By acting as pristine standard rulers, they will provide an independent, direct measurement of the expansion history, telling us if the discrepancy is a mere local illusion caused by our place inside a vast underdensity or a true crack in our cosmological model. And as our maps extend deeper into space, a profound possibility emerges. Will we discover voids so colossal that they finally shatter the cosmological principle? Finding a structure that simply should not exist according to our standard models would be a revolutionary event, forcing a complete reassessment of the universe's fundamental architecture. This is the inevitable shift. Void science is moving from the fringe to the foundation, becoming a central pillar of observational cosmology. The distribution, shape, and growth of these empty regions will provide some of the most stringent tests ever conceived for lambda cold dark matter and its competitors. The answers to our biggest questions are not written in the stars, but in the vast, silent spaces between them, waiting for our new eyes to finally read them.